Now, in my previous video, I said that you can just do example 5.2 yourself. And well, afterwards, I looked at it more carefully and realized something, that 5.2 is actually missing something. The 5.2a is fine. And so please do that yourself. But 5.2b, I want to talk about it some more. Now, 5.2b says that we have a1 equals the half, and then an will be the an minus 1 plus 1/2 to the power n, which when you write out a bunch of numbers, you see some kind of a pattern. Okay, as your book says, a1 is 1/2, a2 is 3/4, and a3 is 7/8, and a4 is 15/16. So you see sort of a pattern. That is, the an is almost 1, but missing 2 to the power nth, 1 over 2 to the power nth, which is fine. Okay, that does appear to be the pattern, but then your book says, okay, therefore that is the answer. That is not good enough, especially in calculus. You got to prove that that is true. Okay, so here's the formula that we are guessing to be right. an, so here's the pattern we observed. Okay, an equals to 1 over 2 to the power n, and the pattern we have seen from a1 to a4. But you got to prove that this is true for all of them. Okay, I mean, just because it's true for the first 4 doesn't mean it's going to be true for the millionth. So so we just need to make sure that it is always true. Now, how do we make sure that this formula fits these conditions always? We simply check it. For example, we know that a1's 1/2. That is, when it's 1 is equal to 1/2, so that's fine. So then what we're going to check is confirm if this is right. So then an equals to this, right? Which is, then we calculate what this thing is and see if we calculate if an minus 1 plus that equals to an. So what is an minus 1? Plus 1/2 to the power n. Is that the formula? Did I write it right? Yeah, that looks right to me. Okay, so we will calculate this thing by this formula now, and see if that will show if the formula works or not. Okay, so what is an minus 1 according to this formula? That would be equal to 1 minus 1 over an minus 1 is 2 to the power n minus 1, and then plus that thing, right? Plus 1 over 2 to the power n. And then, and what does that equal to? That equals to, let me see. What does that equal to? So we're going to do a small amount of algebra here. Now, what is this thing? That is the same as 1 over 2 to the power n. Okay, we'll take the minus 1 out, which is divide by 2. To divide by 2 down here, if you flip it up, it's the same as multiply by 2. So then that becomes minus 2. So this is a minus. Okay, so we become minus 2 plus 1, and then becomes minus 1. So that equals the 1 minus 1 of these things. Okay, there's 2 minus. Okay, so that is 1 minus 2 to the power n. And what is that? That is exactly the definition of an. So we proved that the formula that we guessed, this is just a guess formula, actually does satisfy the entire condition. Okay, from a1 equals to 1/2. Okay, by this formula. So it starts at 1, and then each one afterwards, each an minus 1 will be equal to the an according to the formula, and therefore this particular guess for the formula for an is the right answer. So that's the part that your book missed. And they just guessed it, but they didn't confirm it. See, in calculus, at least, we do need to not just guess. It probably is true, but it doesn't hurt to make sure. You know, in math, we're absolutely sure that we're right. So that's how we prove it. Next, let's consider the limit of a sequence. Now, a sequence has it's just a list of stuff, right? And then it might the stuff can go wherever it wants. However, sometimes a sequence that as the list goes on, all the elements may start focusing on one point and approach some kind of a limit. If that happens, so that everything, like a function, okay, approach some kind of limit instead of just take off or bounce around forever or something, it all start gathering together. And then doesn't ever go away. It gets closer and closer to some point, maybe even reach the point. In that case, we will say the sequence is convergent. If it doesn't converge, we call it divergent. Yeah. So then different sequences might have the ability to diverge or converge. And the official definition is the epsilon definition, the same as the regular limit for functions. That is, you pick a number epsilon bigger than 0, such that if for all the big terms, every single thing, every term that's towards the end, on the tail end, which is infinite, the infinite tail end of the sequence, if you can prove that given any epsilon that's bigger than 0, and the entire tail end will be confined within epsilon of that epsilon limit of the limit, then the sequence converge. That would be the official definition. But unofficially, we just mean that the limit, all the elements of the limit, the tail end, is going to all get together into some point. All right, so then let's go to the next page. Limit by the sequence is, if the limit can be defined by a function like this one, okay, this is like a function, and then in case of a function, this variable will be x, whereas a sequence, the variable is only natural numbers. That's because a sequence is a function whose domain is restricted to natural numbers. Okay, you can totally turn a sequence into a function if the sequence is defined with a exact formula like this instead of recursively. The recursive, you can't write a function directly until you find it. Like in this case, we found the function for it. But if you can't find a function that describes the sequence directly, then the function with its domain restricted to natural numbers would be would be identical to the sequence, and therefore as a result, if you have if a sequence is defined by a function, then if the function as x goes to infinity approaches some limit, then the sequence approaches the same limit, being that the same function. Okay, because being that a sequence is just a function whose domain is restricted to only the whole numbers. All right, whereas a regular function, its domain is all real numbers. So that's the only difference here. All right, now next, let's consider on page 434 the geometric sequence, where you have r is some number to the power n. Where if you have a sequence like that, would it converge or diverge? Well, that depends on whether the sequence is bigger than 1, whether r is bigger than 1 or 1 or equal to 1. If r is 1, then the sequence converges to 1 because it's 1 the whole time, right? But if r is less than 1, then you'll multiply by a number less than 1 all the time, so it will go to 0. The sequence eventually will converge to 0. And if r is bigger than 1, then it just multiply by a number that's bigger than 1. Anytime you multiply by a number bigger than 1, you get bigger, right? So it then just gets bigger and bigger, and then it diverges. So that's the geometric sequence. It depends on whether r is 1, less than 1, or bigger than 1. So next, let's look at some of the limit laws. Now, the limit laws are identical to what we learned in Calculus 1 about regular function limits. The sequence function is just a regular function with its domain restricted, and it behaves the same as a regular function. And therefore, all the limit rules we learned in the past applies with no exceptions. Okay, so that's the theorem 5.2. Please look at it, page 435. But I'm not going to go into details because it's everything you already know. So next, let's practice something called determining convergence and finding the limit of some sequence. Example 5.3. Now for example 5.3, part A is quite straightforward. You'll figure that out. Part B looks a little more confusing until you remember how to do this type of limit. When you have a bunch of powers like that, polynomial on top and bottom, a rational function, the way you take the limit is by dividing out the highest power from the bottom. In this case, you divide it by n to the power 4, and that'll clean everything out nicely. Part C is a bit harder, but then you notice that there's an infinity over infinity situation, which means you're stuck with doing something called the L'Hopital's rule. Please review the L'Hopital's rule if it's rusty, and then and also you also have to take the derivative of 2 to the power x. The derivative of 2 to the power x is equal to 2 to the power x times the natural log of 2. That's a rule in Appendix B. If you can't remember, what is the derivative of b to the power x? It is b to the power x. Okay, it's similar to e, except that you have to multiply it by natural log of b as an adjustment, because is itself times the adjustment, and that's again in Appendix B of the book. So once you remember that, then part C should come out nicely. Now part D is a function that might look familiar to you. The reason it looks familiar is that we did this exact limit at least 4 times in Calculus 1. Okay, and the way to do it, as they will show you if you don't remember. If you don't remember, just go over it again. The trick is to slap on the natural log, and then everything will come out nicely. Do you have to do L'Hopital's rule? Yeah, you might have to also do L'Hopital's rule. So between slapping on the natural log and doing L'Hopital's rule, that limit comes right out. But that's also, all 4 problems are something that you've done in Calculus 1. So this is just a repeat of it. So please do example 5.3, all 4 ABCD for your homework. Next, let's look at theorem 5.3, which says that if you have a continuous function and a function that's reasonably continuous, then should I just say continuous? Then if you have a sequence an, and an eventually converges to some number L, then f of an, assuming it's defined in all the right places, f of an will also converge to f of L. Well, that is being that f is continuous, so that makes sense. And I'm going to skip the proof, but please, because something like this has already been done in Calculus 1. Okay, that is. But do read through the proof to refresh yourself if you want. Now, so let's look at example 5.4. Example 5.4 is a quick example that shows how if a sequence converges to something, then the function of the sequence also converges to the function of the something. It's very short, so I'll let you do that as your homework. And with that, let's move on to the squeeze theorem. The squeeze theorem is identical to the squeeze theorem we learned earlier, which just says that if you have 3 sequences, one is in the middle of the other 2, right? So it's being squeezed, and the other 2 are all converging to the same thing. Okay, they're all going to the one point. So the one in the middle is forced to also converge to the same point. So that's fairly intuitively obvious. There's a proof here, which is also, I believe, identical to the original squeeze theorem in Calculus 1. So I'll let you read that to refresh your memory. And with that, we can look at example 5.5. The only thing hard about using the squeeze theorem is finding something to squeeze it with. So example 5.5, however, is fairly obvious how you're going to squeeze those things. So I will let you do example 5.5 as part of your homework. Next, we're on page 440. Let's consider the bounded sequence. A bounded sequence is exactly what it sounds like. If you can show that all of the sequence is bounded is less than some specific number that you can find or prove, then that would be bounded above. Similarly, if you can find some smaller, lesser number, that all the sequences above it, that is more than the smaller number, then it's called bounded below. If a sequence is bounded both above and below, it is called a bounded sequence. If you can't find any such number to control the sequence, that is, there's always something jumping way out and jumping way down, then it is an unbounded sequence. So if a sequence is convergent, then it is bounded. Yeah, no kidding. That's theorem 5.5. Because if a sequence is convergent, then it'll be within the given epsilon. Remember, that's what convergent means. It'll be given within the epsilon range of the limit. So then, for sure, it's bounded then. And generally speaking, the bounded concept only considers the tail end of the sequence. In the beginning, the sequence might be very big. We don't really care. The question is, if it approaches something, then we know it's bounded within the epsilon, plus or minus epsilon of the limit L. Now, having said that, let's look at the next thing. Another idea. If a sequence is increasing all the time, okay, along the tail end, remember, we don't care what the sequence does in the beginning, okay? The first 1,000,000 terms, for first 1,000,000 terms, it doesn't really concern us. The question is, what does the tail end does? Because the tail end is infinite, okay? The first part of the sequence is only finite. So what does the tail end do? If the tail end is a sequence is increasing, if all the members along the tail end, is bigger, okay? At least no smaller. That is, an is less than or equal to an plus 1. If that situation happens, the sequence is called increasing. On the other hand, if it gets less, if an is bigger than an plus 1 the whole time along the tail end, then it's called decreasing. A sequence that, whether it's decreasing or increasing, such a sequence is called the monotone. And with that, we have come to the monotone convergence theorem, which says if you have a bounded sequence, okay, so it's bounded, and it also is monotone, so that it's either increasing or decreasing the whole time of the tail end. If that is the case, then the sequence has to be convergent. And you would think that seems like a pretty obvious fact. Like, for example, look at the picture that's on your book. Okay, here's the sequence. Is monotone increasing and it's stuck on top. It can't get any higher. So then, then it has nowhere to go but to converge, right? It's going to converge somewhere because it can't go down and it can't go any higher, right? However, well, the book doesn't provide a proof for it. I'm pretty sure there's a similar concept in Calculus 1, but I can't think of it right now, being that your book doesn't want to prove it, and neither do I. So let's move on and just use the monotone convergence theorem and not worry about the proof. Now now we have come to example 5.6. The first thing, all right. Example 5.6. First, let's look at part A, where we have the sequence here, which is 4n over n factorial. Well, does this thing converge? If it does, where does it converge to? What's the limit? Well, first, we are going to figure out if the sequence is monotone or not. That is it increasing or decreasing? And we can show that the sequence is going to be something. What is this? Decreasing, I guess. Yeah, and to show the sequence decreasing, what we're going to show is that eventually an plus 1 is going to be less than or equal to an, right? It just each new term is smaller. But how do we show that? So we're going to manipulate this algebra, okay? So we're going to do an plus 1, plug that in. That equals to 4 to the power n plus 1 over n plus 1 factorial. Remember what the factorial is? A factorial for example, let's say if you want to figure out what 5 factorial is, the 5 factorial is 5 factorial. It is 5 times 4 times 3 times 2 times 1, okay, which is like, I don't know, 20 times 6, 120, that sort of thing. And the factorial button is also in your calculator if you need to calculate it. As you can see, the way this works, the factorial increases rather quickly. But in any case, that's what we're dealing with right now, is the factorial. Okay, so we'll manipulate this thing to make it look a bit like this one, the ANs, that is, and see how they compare. That would be, if we factor out the 4, and then the n plus 1, and then that we have left with n factorial. Remember, n factorial times n plus 1 becomes n plus 1 factorial due to its definition. In the meantime, so we'll take the 4 out, so we have only 4n here. And what is this? This is exactly an. See, this thing is an. So that equals to 4 over n plus 1 times an. Now this thing, for if, as you look at n, when n is smaller, like 1 or something, this number is bigger than 1, which makes an bigger than an plus 1 bigger than an. However, the second this number goes big, gets to be 3 or bigger, then this whole fraction becomes 1 or bigger, and which means the relationship will be less than an, okay, because you have a fraction that's less than 1. So then multiplied by an is going to be less than an itself for all n bigger than or equal to 3. And therefore, this sequence an is a monotone decreasing sequence. Now that we know it's decreasing, which means and it's also bounded, right? Because it's bounded simply because an is bigger than 0. Okay, so it's bounded by 0. All an is bigger than 0 because all the numbers here are positive. So so now we know that it's decreasing and bounded. Therefore, the limit exists. The limit might exist, but how are we going to calculate it? That is not going to be so easy based on our past experience, because this is a function, and normally we'd be able to use a function of this thing and see where the function goes, right? Maybe apply the L'Hopital's rule if necessary. But this one, there is no function for the factorial, okay? The factorial only applies to natural numbers, so you can't slap on a function, which means you can't do the L'Hopital's rule, and you are stuck. However, if you turn the page, you realize there's a neat trick that they can use for this kind of thing. And so let's look at the neat trick that they use. What happens is that you argue that the limit of an plus 1, okay, as n goes to infinity, is the same as the limit of an. Why is that? Because it's the same sequence. N is just going to infinity anyway, so it doesn't matter which one you're talking about, okay? So n, yeah, see, they're the same thing, identical, because n is approaching infinity, and therefore, so let's call this equal to L, okay? Let's call the limit L, because we already established that the limit exists. Now, it's knowing that a equals to L, that is, we'll write down this relationship. That is an. So then, what was that? Yeah. So then what does this equal to? This is equal to limit n approach infinity. We'll copy this down. An is this thing, okay? 4 over n plus 1, okay? An is equal to the limit of an itself. And approach infinity. Now at this point, then you notice that as we remember, the limit rule applies. The normal limit rule applies to everything. So this is the limit of each term, right? Which we equal the limit of this. So let's call the limit of this equal to, this is of course L. And then that equals the limit of 4 over n plus 1 as n approach infinity times the limit of an approach infinity. And that also equals to L. What does that mean? That means that, and what is that? The limit as n approach infinity, n is approaching infinity, of this thing is 0, which means 0. So rewriting this funny looking thing, we get 0, okay, that's that, this approach 0, times L equals to L. That means this equation shows that L equal to 0, okay, because 0 times L is 0, so L equal to 0. And that is the limit of an. It eventually approaches 0. So you can see there's a neat trick that you use if you have the explicit formula for the an, that to find the limit. You just make a very interesting argument, and then it comes out that way. So that's the answer to part A. Next, let's look at part B of example, whatever this is, 5.6. The part B is a recursively defined sequence. Recursively defined things usually are harder, and this one looks even worse than harder. I mean, look at this. You have to you have to divide by an each time. So then recursive means that each new sequence member is defined by the one right before. Okay, so you have to calculate each one to plug it in. You can't just calculate one and then you get a set formula and plug it in, everything pours out. There's no pouring out here. You have to do each one before you do the next one. So if you need to figure out what the thousandth term is, you have to do all 999 first. Whereas this equation, if you need to know what the thousandth sequence term is, just plug in 1,000 and you're done. Right? So the recursively defined things are more complicated, and this one's even worse because if you want to see, oh, what does the sequence look like? So we'll plug in a few numbers and work on each one and see what they are. Well, your book conveniently showed us the first 4 terms, and look at that. It gets bad fast, right? And then your fractions are going to get bigger and bigger, and eventually you'll wear your hand just writing it, or not to mention punching it into the calculator. So we're going to stop right there. However, you do notice that the numbers seems to be going down and approaching 1, see? Because the fraction, while it gets more of a headache, it does seem to be very close with the top number slightly bigger than the denominator, right? So then it's possible that it's bounded by 1 if this pattern continues. Well, is it bounded by 1? Well, being that we are completely clueless as to what to do, we're going to investigate that situation, see where it leads us. So we are going to assume, we're going to say, is it bounded by 1? So let's say this thing is eventually going to be bigger than or equal to 1. So we write this down, an over 2 plus 1 over 2an. Let's say it is what? Bigger than or equal to 1, okay? And see where it leads us. Because the reason we're doing that, because we don't know what else to do. Okay, this thing is completely puzzling and doesn't look like anything we ever know. And no law applies. We can't use any limit laws or function or continuity, nothing. Okay, we're stuck. So being that we're stuck, we're going to work on manipulate this and see if it leads to anything. It might not. That's the way it is. So then we redo this fraction, which becomes, of course, that becomes, well, okay, common denominator, that is 2an. So then it becomes an squared here, n squared, plus, what is that? That's just 1, right? Yeah. Okay, plus 1, and that is going to be bigger than equal to 1, which doesn't get us very far. And so the next step we're going to say is therefore then an, oops, sorry. an squared plus 1 is bigger than or equal to 2an. Now we don't know if this is true. We're just saying if this is true, what would happen? Let's see where it leads us. Okay, we're exploring a trail. We don't know if it's gonna, that trail is just some random place that gets us nowhere, or is it gonna lead us to where we're going? It's just a random trail, and it's basically the only trail we can think of right now. So we have that, and then my n is too long. All right. So, and then we have that remind you of what? So that can be rewritten as the perfect square, an squared minus 2an plus 1 is bigger than or equal to 0, which this is just an minus 1 squared. Is bigger than or equal to 0. Now at this point, you notice that this fact always stands, right? This equation leads to this, but the thing is, this is always true because it's a square. Squares are always bigger than 0, which means, but this directly comes from here, which means this is always true also. So therefore, we have just stumbled on the proof that this sequence is bounded below by 1. Yeah. Okay. Now that we know that it's bounded below, we have to also show that it's decreasing, because if it isn't decreasing, then being bounded below means nothing, because it's just going to take off on top. Or, I mean, it might. So to show that it is decreasing, we're going to use this fact. Okay. So, being that it's bounded by 1, below by 1, so in other words, an squared is bigger than or equal to 1, and we're going to use another trick to slap another trick on it. That means that an squared plus 1 is, let's see, let me make sure I get the inequalities right. So an is bounded by 1, that is 1 less than an squared. No. All right. Now, we have just shown that each an is bigger than or equal to 1, which means that an squared, this is also true for an squared. Because a number that's bigger than 1 when it multiplied by itself, being that it's bigger than 1, is still bigger than 1. So an squared is also bigger than 1. And then, so then we have, what? Next, we are going to add an squared to both sides of the inequality. Okay, so then we have an squared plus 1 on this side is less than or equal to 2 of an squared, because we're adding 1 to each side. So that inequality still holds. And then we're going to divide it by something. Let's see. All right, next we are going to divide everything by 2an. So 2an, and this is, we're pulling a very slick trick here. All right, so then we divide it, and then what do we have? Then we have rewriting it, that equals to an over 2 for the first term, right? Plus 1 over 2an. That's the second term, less than or equal to, that is just an. That's about it. That's just an. Okay, and what is that thing? That thing is just, we have constructed this thing with a very slick trick. It's exactly the definition of an plus 1. So we'll write that down. That equals an plus 1, which, what did I just show? I just showed that an plus 1 is less than or equal to an. See? A super slick trick. That, well, the trick only applies to this problem, though. And it might not apply anywhere else, but it just happens to work out this way. So it's very beautiful and slick. It happens in, especially in algebra. Sometimes you do some weird thing, wander around, and suddenly there's the answer. You know, it's like finding gold. It came out of almost nowhere. So then we have now proved that this thing is decreasing. Now, we have proved that it's decreasing and bounded, and therefore it converges by the monotone convergence theorem. So the last thing we need to do is figure out, well, what does it converge to? And to do that, we are going to apply that same trick that we did earlier. Somehow, we say that the limit of an plus 1, okay, that is the same as the limit of an, because they both go to L, right? What's the diff? There's no diff. And then somehow manipulate L to come out that way. Okay. So we are going to slap the limit sign on all of these things. Limit here, limit here, limit here. Okay, so what do we get? We get this thing approaches to limit, right? Equals to that thing approaches to the same limit over 2 plus 1 over 2 times the limit. That's it. This is the equation. And if you solve this simple equation, you get some kind of an answer, which is eventually you get quadratic equation, yeah? And you come up with an answer of L equal to plus or minus 1. Well, being that it can't be minus because our sequence is positive, I believe. Yeah, it is. It's not going to get negative ever. So the limit is just 1. Okay, the negative, it doesn't go to 2 limits. It's not possible to go to 2 limits. Convergence means you converge to 1 limit. And so the limit is 1, and that concludes the story. As you can see, the the sequence, to calculate sequences, you a lot of times have to be inventive or lucky or just try different things, trying, well, weird tricks really to find the answer. And that's why sometimes students find sequences very hard. But in reality, what you do is just hunt for the trick, okay? And if you can't think of the trick, then it's time to get a hint. See if the book can give you a hint as to how to do this, how to pull this off. Okay, so with that, we have come to the end of this video. I will assign homework for next time because I'm not done preparing it yet. We will also do the student project as part of your homework, where you're supposed to calculate the Fibonacci numbers. I don't know what the Fibonacci numbers are good for, even though they are famous. So as a calculus student, you should probably know about them so that you don't look ignorant. But otherwise, I have never seen what the purpose is, okay? Even though the sequence has a name. But anyway, we're going to calculate the exact formula for the Fibonacci numbers in the next video, which is quite interesting actually, because it uses some slick trick to pull it off. That a trick that you probably can't use for any other problem, but each tough sequence problem, there's somebody dug out some slick trick, and then you follow it, and there comes your answer.